All right. Hey, everybody. So today we're talking about condensed mathematics. And I guess maybe I should start out with the following disclaimer. Oh dear, I'm in the wrong notebook. I need to go to the food for thought one. All right. Can everyone see that all right? Okay. So the things, so let me start out by telling you what I'm not going to tell you about, which is going to be all of these various sort of buzzwordy looking things that are some of the jargon in algebra. And so if you like these words, or if you want to know more, I can refer you to Peter Scholz's notes on condensed mathematics, which are just on his website. I'll also be giving a talk at the RTG Colloquium tomorrow, if you want to come to that. But what I want to do in this talk is just give an sort of very general introduction to what the idea is. So let's recall some algebra. So I want to talk. So yeah, and if anyone has any questions, please feel free to interrupt. But so let me just recall some terminology. So we want to talk about exact sequences. So let's consider some modules over our favorite ring. Sequence and with this notation is exact if the image of map coming in is equal to the kernel of the map going out. And then most of the time when we notate it, we won't even write F and, oh dear. We won't even write F and G there. We'll just write this, and just the fact that it's here will tell you that it's exact. What else do we do? Hom Mn is a set of homomorphisms from M to N. So these are module homomorphisms. One thing I'm going to want to do is take various like commutative diagrams and quote unquote apply the Hom. So what it means to apply Hom is for every map M to N, I'm going to get this like pullback map, which is from Hom N applying the Hom functor for P. The map will be from Hom N P to Hom MP. And that map is just G goes to G composed with F. And then the last thing I want to recall is something you may have or may not have seen in an algebra qual is this thing called ext. And so I'm only ever going to use the first ext. So I'm going to define that here. And what it is ext is the set of, what's that? Someone say something? Nope. Okay. Ext is a set of short exact sequences. So we're going, say, 0 to M to P to N to 0. And so, again, you recall this kernel mod image thing is going to mean that this thing is injective. This thing is surjective. And this ext is ext. It's a group, even a module. And so we're considering equivalence classes of these. And what's the equivalence? The equivalence is well, commutative diagrams that look like this, where these two things are the ID, and this is an isomorphism. Okay. And maybe we'll call these compatible.
Hi. I wrote this as a in the chat to be quiet, but Vaki's saying to speak up for the recording.
Yeah.
You should switch M and N. A small nitpick. It's extensions of M by N. So in the
this to be switched.
Yeah.
Yeah. Sorry about that. Yeah. Okay. So I've recalled my terminology. Now I want to talk about sort of a high-level thing, which is how do algebraists actually prove theorems? And if you look at a lot of different algebra proofs, you'll notice a lot of similarities, even in sort of slightly disparate kind of areas of algebra. So let me state a theorem that I want to prove, which is, so I have a short exact sequence, which will be n, m goes to m goes to m mod n. And so I want to say this short exact sequence splits. So if you remember, splits means that m is a direct sum of these two, or alternatively that this map has a section, or this map has a section. That is a map back that when you compose them, they get to be the identity. So this is going to split if and only if, or it's going to split if this X group, m over n, with n equals 0. And so how do you prove this? So how do algebra people prove this? Well, they don't actually have X defined in a way that I just defined it. They have it in something slightly different, which is a long exact sequence. So let's do the long exact sequence. So what are we going to do? We're going to take the HOM, apply the HOM, like I was talking about, and I'm going to take HOM, the HOM, the homomorphisms going into N. So, and then what the sort of key lemma is, which is really at its core is the snake lemma. But I'm sort of going to take it as a black box, is that, so what we're going to get is we're going to get an exact sequence, which, and then I'm going to have HOM from M to N. And so the arrows are going in the opposite direction. You noticed I had an arrow up here going from M to N. Here it goes from N to M. So it's switched. So I wanted it to switch. So then we'll go HOM N, N. And then the lemma, which is, again, under the covers is the snake lemma, is that I now have another homomorphism to the X'd module, M over N. Is that right? This is switched. M over N, M, X'd 1, M, N. And then the sequence continues, and it continues for as long as you go. You can define X2, don't worry about what X2 is. But the point is that, so by assumption, this equals 0, which means that this map is a surjection, or no, it doesn't mean, well, of course that's a surjection, it's mapped to 0. It means that this map is a surjection because the kernel of this map, which is everything, which is the whole thing of this hom nn, is equal to the image of, let's see, this map right here. And so what that means, so maybe I'll write that down here. We have hom mn surjecting onto hom nn. And what we can do is, so the identity map from n to n is something that's in here. So we choose a lift of that, call it f. But then this map f, by the definition of what we had up here, is just, well, now my g's and f's are mixed up, but it's what it's going to be is f maps to f composed with, well, it was this guy right here. Maybe I'll call this I. So f maps to f composed with I. And what does that mean? That means that f composed with I is the identity, which is exactly the same thing as saying that there's a section, there's a map back, and thus the sequence splits. And so, okay, if there are any questions about that, maybe now would be a good time to speak up. Maybe I'll wait a second. Okay, so the significant thing, as I've written sort of at the bottom here, is that like when you're thinking about like what we used to prove this, we used a trick. We used, I mean, at the end of the day, it's this long exact sequence and the snake lemma, but it's something that quote unquote has content. Whereas if you see a lot of parts of proofs in algebra, it'll be just reinterpreting like various terms in category theory as other terms in category theory, and then the thing that you wanted to prove becomes obvious after you've reinterpreted it. And so this sort of method, this trick, is it's something that's pervasive. It's all over the place in algebra. And maybe just to convince you of this, let me just sort of throw out an advertisement there that our current department chair, James McKernan, won a breakthrough prize based on a proof which at its very core uses a similar argument to this. The things aren't the same, right? But the proof looks more or less the same. What you do is you have, it's a proof by induction on the dimension of some varieties or manifolds or something. And in this term, you have something that's of dimension n, and on this term, you have something that's of dimension n plus 1. And you want to show that there are enough elements in here. So what you do is you finagle things around so that this thing vanishes, then this is surjective, and then your thing in dimension n plus 1 has enough elements in it. And the bulk of the proof is understanding all of the language that you need to sort of finagle it into working, which I can't say I understand the whole proof, but the sort of skeleton of it and the skeleton of lots and lots and lots of other proofs in algebra and related things is very similar. So hopefully now you're convinced about the usefulness of this sort of way of thinking. And so if we're convinced that a trick is useful, we want to prove, we want to be able to use it in its most general setting. And for this trick, the most general setting is what's called an abelian category. So when I say abelian category, you should think an abelian category is a category, and it's a category that looks like abelian groups. So I'm not going to give you precisely every single condition that you have to define an abelian category. There are like 12, but let me just put in here like some of the things that you need. You need kernels, for example, and the kernels need to work like they work in abelian groups. So like the kernel of a map of abelian groups is an abelian group. So for example, rings are right out, right? The kernel of a map of rings is an ideal. It's not necessarily a ring. Co-kernels. So if you don't remember what a co-kernel is, if you have a map like this, the co-kernel, say of sets or abelian groups, the co-kernel of F is the codomain mod the image. And somehow in a category theory sense, this is dual, as they say, to the kernel. What else do you need? You need direct sums, and they need to exist, and they need to behave nicely. What else do you need? You need injective and surjective. Are exactly what they should be. So this is another thing. So rings don't work here. So this is a question you may or may not have seen on the algebra exam, but there's a map. You can construct a map from Z to Q that, in the sense of category theory, should be a surjective map, but it's not surjective because it's a map from Z to Q. And so again, rings don't work here, but modules over any ring will work. And whoops. And then the Hom sets of two objects, I guess, or groups or whatever, modules, are an abelian group. Particularly when I have the Hom, say, I don't know, of two abelian groups A and B, right? What's the group law? F plus G. Well, it's defined to be F plus G of X is equal to F of X plus G of X. So when you have something like this, you can make your Hom sets be abelian groups, and that's sort of one of the key parts of being an abelian category. So I mentioned, and then maybe the last thing I'll just mention as an advertisement for abelian categories is things you can prove with them. For example, class field theory. And so when you prove class field theory using an approach which again is very similar to this proof here, what you do is you spend like a lot of time like developing the theory of the abelian category that you want to work with, and then your proofs after that don't take a ton of time. And I mentioned the minimal model program, which is what James McKernan works on or worked on or something. So abelian categories are nice, and they're all over algebra. So what do we want? Well, so yeah. So now what we want to do is, so what's the problem with abelian categories? Well, there are two problems. Number one is you need all of these things to be true. And number two is you need some sort of vanishing theorem. So you need some, if I didn't have this x being 0, the proof like totally doesn't work. So, and even if I could like write down what this group was, but it wasn't 0, the proof still doesn't work, because a priori, I don't know what exactly this map looks like. It's like somehow like 5 levels deep in the formalism. So I want to think about topology. I want to think about analysis, and I want to think about topological groups. And the groups that I want to talk about today are going to be LCA groups. So by LCA, I mean locally compact abelian groups. And there are sort of more general kind of contexts like Banach spaces that we can maybe do this, well, not maybe, we can do the things that we're going to do today in, but right now I just want to stick with locally compact abelian groups. So if you don't remember about locally compact abelian groups, they are sort of the foundation for Fourier theory. But there's a problem when we're dealing with things that have topologies on them, and we're trying to do algebra. And the problem is exactly what I've written here, is that topological groups are not an abelian category. And I want to demonstrate that to you. So let me talk about a topological group. That's a locally compact abelian group, which would be R. The group of real numbers. So this is maybe one of the most basic locally compact abelian groups that you can think of. And if you've studied locally compact abelian groups, I think even in some of their like some theorems and like R sort of shows up. So it's very fundamental. Okay, maybe I'll stop trying to convince you that the real numbers are fundamental. And I'll tell you about a map of locally compact abelian groups. And what I want to do is I want to map R with the discrete topology to R with the usual topology. So the metric topology, maybe. So, okay. What do we have? This is a topological group. It's a locally compact abelian group. This is also a topological group. It's a locally compact abelian group. And my map is going to be the identity map. And that map is definitely continuous. So if I have an open set over here, and I guess I'll pull that back over to here. Well, it's just going to be the same set, and because I have the discrete topology, every set is open. So the inverse image of any open set is definitely open. But now I want to ask you, what is the kernel of this map? What is the co-kernel? That question is, I mean, I don't know if you look at this map and you say, oh, I think this map, this is a surjective map, this is an injective map. What should its kernel be? What should its co-kernel be? I don't know about you, but none of those things are obvious to me. So we don't have kernels and co-kernels working out just like abelian groups. We do have some things like Hom sets will be abelian groups, but if we don't have nice kernels of maps, then we just can't have an abelian category. And so I think for years and years and years, people thought that doing algebra in a context like locally compact abelian groups just wouldn't be very successful. So
I have a question.
yeah.
Why would kernels be tough?
So what is the kernel of this map?
Well, what gets sent to the identity of R. If R is with addition, then it would just be the set 0.
Okay, sure. What about?
If I could comment, I
Sure.
think more the awkwardness, Fatsa, is that the kernel is that if you try to define kernel and co-kernel in the only reasonable way here, like you would guess, you would want them both to be 0 here. But so you have a map here where kernel is 0, co-kernel is 0, but it's not an isomorphism, and that's the awkwardness.
I think I meant to say that too. Yeah. So this is just to repeat what Alex said. Yeah. So this is definitely not an isomorphism, but just as a group, the kernel and the co-kernel are both 0 because it's the identity map. And so, yeah.
Right. I guess it comes from the fact that bijective continuous does not imply bicontinuous.
Yeah, it basically does, I think.
Yeah, and I always thought the awkward thing with non-abelian stuff is co-kernels. Kernels, I think, are usually fine. Like the kernel of a topological homomorphism should be a topological group, right?
Yeah. Well, and maybe I won't. I don't want to spoil it too much, but it turns out that the weirdness in this one is going to be in the co-kernel of the map. But we're going to end up being able to define it like we want to. So maybe I'll go on to the solution to our problem.
Thank you.
Which is the Cantor set. So let's talk about totally disconnected sets. A set is totally disconnected if each point is its own connected component. And so the main example of this is the Cantor set. So the way you make the Cantor set, maybe I'll just remind everyone, you're taking the sort of successive intersections of, you have the interval, and then the first and last third of the interval, and then the first and last thirds of each of those thirds, and so on and so on and so on. And what you can show is that the Cantor set is homeomorphic to the product from I equals 1 to infinity of 0 and 1, i.e. all binary sequences. So why is it all binary sequences? Well, the best way for me to show you this is to show you a picture. So the picture is going to be, maybe we're going to start here, and then we have to pick any element of the Cantor set. What you have to do is you have to pick one of the 2/3 that the Cantor set, like that the, I guess, the ith iteration of the Cantor set is in each time. So first I might pick this one, and then maybe I'll pick this one, and then this one, and then there will be another choice in here, and another choice, and another choice, and another choice. And you have countably many of these to do. And at the end, what you'll be left with is a binary sequence, which is just in here. So that's, by Cantor's diagonal argument, that's a proof that the Cantor set is uncountable. It's interesting. And it's also totally disconnected. And I guess maybe what the way you see it's totally disconnected is that any point is going to sort of differ at some level from any other point by some like positive distance. So it's totally disconnected as a subset of the real numbers. Some other totally disconnected sets that you have heard of before, for example, the rational numbers. The rational numbers completed with the p-adic metric, so the p-adic numbers. Also the irrational numbers. So the way you prove it for the rational and the irrational numbers is you notice that there's a real number in between each of them. So if you just take the subspace topology with the real numbers, it's going to end up being totally disconnected. Okay. So why? So this is the thing. It's like we have we have this problem with not being able in algebra to reason about the real numbers and to reason about topological things. And I'm telling you that the solution is going to be totally disconnected sets. So why might totally disconnected sets be like telling us about the real numbers? So let's think about what are the real numbers. So the real numbers, if you remember from what you learned in grade school, like the way you learn about it is all possible, sequences of all possible, I guess, all possible sequences of I guess it's not binary, but it's 10 digit things, which or 10 digit, all possible sequences of 10 digit numbers, I guess. Does someone want to say something?
Oh, decimal? I don't know. It's just a bad joke, or it's not a joke. It's the truth.
All possible decimal sequences. Anyways, you have this, but then you also have some of these things that, so I guess I'm considering 0, 1 here, because I want everything, I want them all to start at the same place, but you can just as easily consider the real line. And then, but I want there to be an equivalence relation, and that equivalence relation is when I have a string of 9s, well, that's actually going to be the same number as the thing where I sort of up this digit and put zeros after it. And this is, I don't know, this is something that's, I guess, confusing for grade schoolers and middle schoolers or across the world. But like what this shows us is that the interval, I guess, is, well, it's a quotient of a totally disconnected set. So all of this, I spent all this time talking to you to justify that totally disconnected sets might be somehow a way that we can learn about these topological things or these, or just the geometry over the real numbers. And so we're going to see a little bit of what that looks like for locally compact abelian groups. So let's make a big definition. So
is that equality you wrote actually a homeomorphism? Like, is it actually that quotient?
I believe so.
Okay, yeah, I wasn't sure.
I don't have a proof. So this is more of a heuristic. but
yeah,
this is sort of the idea that ends up getting used and made more precise in a more algebraic way that I'm not going to explain today. But
okay, cool.
So okay, so so a condensed set is an assignment. So for every totally disconnected set S, we are getting a set. So my condensed set is going to be T. So T of S will be the value of my condensed set. I can't say this is a function because the set of sets is too big to have functions on, but I'm not going to say the words what it actually is. But not only do I have a set for every totally disconnected set, I also have a map for every map of totally disconnected sets. So T of F goes to T of S2 to T of S1. And just like my HOM earlier, the direction of the arrows is going to flip. And so then I'm subject to a bunch of compatibility conditions. I don't want to talk too much about these, but it's basic naturality things, right? Identity goes to identity, compositions go to compositions, and then each condensed set comes with an underlying set, which, so if star is the set containing one element, T of star is the underlying set. Of T. So what you want to think of a condensed set is it's a set, but somehow we can evaluate it not, when we spit in the point, we get back our original set, but we can also put in other totally disconnected sets, which might be finite or might be infinite. So let's do an example. So for X, any topological space, the assignment S to continuous maps from S to X is a condensed set. And now you see why I wanted my arrows to reverse, because the arrows are going to reverse when I take the condensed sets out of my set, just like what happened with HOM. So this is going to be denoted X underbar. And so now I'm going to make another quick definition. A condensed abelian group. And then I can also do this for, yes?
Could you go back to the last page for just a second? I want to see something.
So
I'm just wondering about this Roman numeral 1, the big Roman numeral 1. Should that be the?
Yes.
Okay, I guess, yeah. Little 2 and big 1 seem to be in conflict for me. Is this supposed to be contravariant? Because then big 1 would be good, but little 2 would be bad if it's covariant.
This is a contravariant thing. I may have done this
okay,
wrong.
cool. So little 2
maybe backward.
Okay, yeah. All right. Carry on. Sorry about that.
Sorry. Yeah, no, it's definitely a contravariant thing, and I can do this for rings, modules, so about etc. Is exactly a condensed set, but instead of assigning totally disconnected sets to sets, I'm just going to put by abelian groups or rings or modules over a ring, right? Whatever. And then again, for a topological abelian group, G underbar is a condensed group. Abelian group. The group is, the group law is exactly what you think it is. It's the same thing as before, where f plus g of x equals f of x plus g of x. Okay, so let's go back to our example. So what happens when we condensify? Well, right here, we're going to get the continuous maps from a totally disconnected set to R. So that's what's going to happen to this guy. And then what's going to happen to this guy? So what are the continuous maps from S to the discrete topology? Well, that's actually the same as the locally constant maps, because something's going to be continuous for that discrete topology. It's got to be locally constant. And so locally constant maps happen to be continuous. So this is actually an injection. And I can write a 0 there. And it will have this co-kernel, will be this quotient, which is the continuous maps from S to R mod the locally constant maps from S to R. And then, because that's a quotient, that'll be surjective. And I'll call this quotient Q. And the thing that I want to point out is that on the underlying sets, the underlying set of Q is 0. Why? Because the underlying set, the set of maps from a point, and the locally constant maps from a point to R are actually the same as continuous maps. So locally constant is the exact same thing as continuous. Forgive my sort of lazy notation here. And in fact, on any finite set, we also have this. Locally constant and continuous are the same thing, but only when we get to the infinite sets. So do we see a difference? For example, let's say I have the inclusion of Q into R. So I'm evaluating this guy is not locally constant, but it is continuous. So things of the form Q go by the technical term non-quasi-separated, although I like to just think of them as just weird. And so they're these things where they take values on infinite sets but not finite sets, and apparently that is just the thing you need to make it so that kernels and co-kernels work. So let me go now. So Clausen and Schulze, who are sort of the people, some of the people behind condensed mathematics. So condensed abelian groups, what they have shown is that the category of condensed abelian groups is an abelian category. Which is very cool, because that gives us the opportunity well, it gives us the opportunity to run the same argument that I did at the very beginning. But I said we need another ingredient to do that, which is a vanishing theorem. So here's a vanishing theorem. I won't prove this theorem, but you can prove it using just what you know about locally compact abelian groups. So what is that theorem? So the homomorphisms, so in this case, HOM is going to be homomorphisms of condensed abelian groups, which I haven't quite defined, but they sort of come from, at least in the case where, in a case where a condensed abelian group comes from a usual abelian group, the homomorphisms are exactly those homomorphisms of abelian groups. So in this case, that's all that happens here. But so if A is a compact group, there are no homomorphisms from that to R. And so the way you think about this is compact, but its image also has to be invariant to scaling in R by the fact that we're in a sort of topological group setting, so it has to be 0. Also, there are no maps from R to a discrete group, and then there are similar things about these X'd things, and so we're only going to use X1, but there's ways to define this higher X, and I'm just going to gloss over that. So here's a theorem that we can prove, and we're going to end up using basically the same argument. So the theorem is that every extension of locally compact abelian groups, 0 goes to R, goes to some group, goes to R, and this would be surjective, that would be injective. Every single one of them splits, i.e. G is going to be R2. So how do you prove this? So now we can write a short exact sequence in the category of condensed abelian groups.
Just to
what is
clarify,
that? Yes.
The maps in this theorem are just pedestrian old continuous homomorphisms, right?
Well, they're going to be condensed. They're going to be condensed morphisms.
Okay.
But it doesn't make a difference because all of the groups are abelian groups, and all of the condensed morphisms come from abelian morphisms. So if you want to think of them as pedestrian abelian group morphisms,
like in fancy terms, Vaki, like considering an abelian group as a condensed group is a fully faithful thing.
Yes.
Gotcha.
Fully faithful is the word that I'm not saying.
Gotcha. Okay, cool.
So the exact sequence that I wanted to talk about was I'm going to inject the, so you should think about this as pedestrian abelian groups, but it's actually condensed abelian groups. So I'm just using the fact that S1 is R mod Z, and that's now a short exact sequence. And so then what I do is I apply HOM with R, and then what's going to happen is I'm going to get this same long exact sequence, R Z R goes to X1 S1 R X1 R, which, if you remember, that was the thing from the very beginning, X1 Z R, and that goes on, and I've stopped writing all of the underbars, but you can pretend that they're still there. And what do I need to say? Well, if I look at my theorem, let's see, this part will apply to, or I guess maybe this part will apply to this guy, so this is going to equal 0. And this is going to equal 0. So now I have 0, and the kernel of the 0 map is equal to the image. And what that's going to mean here is that the guy in the middle, which is this guy, I don't know if that picture helped, but what that's going to mean is that for this to be an exact sequence, this guy is equal to 0. And so then what you need to do is you need to repeat the proof exactly verbatim that I gave at the beginning, which I wasn't going to do and I'm not going to do. But when the x1 is 0, then all of these extensions will split. And so that is, and so that concludes the proof. And well, actually, it doesn't conclude the proof. What you have to do is, last step is to take underlying sets. Okay. That, I think, concludes everything I wanted to get through. I guess maybe as a shout out, there should be, the people who are doing this are trying to do tricks like these for things like Banach spaces over QP and Banach spaces over R and all sorts of fun stuff. So
cool. All right, everyone, let's thank the speaker.
Yeah, thanks everybody.
Right, and I think since we're over time, let's conduct questions over the Gather Town. So if you are interested in asking the speaker questions, please get onto the Gather Town, and we'll see you guys next week. Thank you very much.